now you can understand, isn't it? Axial modes, what are this, right? You can see these two, right? Frequency axial modes, right? Axial mode 1, axial mode 2, you can distinguish. Axial modes will depend upon the cavity length, right? So, standing waves will form axial modes, and standing wave pattern will allow light to reflect it without losses as it is. Okay. Of course, transmission of the mirror is a loss anyway. If the mirror is not highly reflecting, but transmitting, means there will be some loss, that is fine. But due to the destructive interference, the loss is not there. Okay. So, we will keep oscillating theoretically for, right, if both the reflectors are highly reflecting mirrors, the generated electromagnetic wave will keep oscillating, is not it. So, basically feedback is provided to that within that cavity. Okay. Now, we were discussing about in the last class. Okay, sorry, I will keep this. So, in the last class we were talking about how to achieve population inversion or for effective amplification of light, which is possible due to the stimulated emission. However, at in the normal, right, condition, thermal equilibrium, spontaneous emission is quite prevalent, quite dominant, and hence we will not be able to observe light amplification as it is, right. Although there will be stimulated emission, when spontaneous emission, there is a chance that stimulated emission can also take place. However, that may not be dominant enough, okay, as compared to spontaneous. So, what we will see is a spontaneous emission, and we will not be able to see light amplification as such. And for achieving a dominant, right, factor in terms of light amplification, we need to, right, allow right, dominant stimulated emission basically, and for that indirectly, for that light amplification and very effective, right, stimulated emission, the population inversion should be there. What it means population inversion? So, okay, maybe I will write down. So, for light amplification, right, of course, amplification is due to stimulated emission of radiation. Correct, stimulated emission amplification, and for this amplification to achieve, right, we need population inversion. Between two energy levels, right, where we want amplification to come into picture, right. Population inversion means this is energy level, let us say E1 and E2. Then if we are considering population inversion between these two energy levels with N1 and N2 as the population of excited atoms or population of atoms or ground level atoms or excited atoms, electrons, right, based on that. So, N2, if it is greater than N1, if we can achieve, right, it will allow, it is nothing but the population inversion, and that in turn will allow amplification, right. However, as we also learn that when we are considering two level energy systems, right, population inversion is not possible, okay, because we learnt already, right, the stimulated emission coefficients are equal, absorption and stimulated emission coefficients are equal. So, we will not be able to achieve this. So, for achieving right n population inversion, we use slightly modified approach. Instead of two level energy system, we use materials which can allow using 3 level energy system to achieve population inversion, okay, 3 level or 4 level. Okay. So, if I quickly describe what it means by 3 level or 4 level. Okay, okay. So, let us say we use okay, pumping light. Okay. So, first I will describe okay. So, say there are 3 energy levels. Okay. So, say E1, this is E2, this is E3, correct. Now, these energy levels are such that when this is E1 is a ground level, E3 is the upper level, and E2 is the intermediate level. And if we use a light which is having a frequency matching with h nu 3 3 1, okay, h nu 3 1 or 1 3, correct, 1 3, meaning the photon energy is 3 minus E 1, correct. If we use a photon with the frequency matching with this h nu equal to E 3 minus E 1 energy, what will happen? The ground level atoms over here will absorb this, it will go to the upper energy level, okay, E 3. Now, the condition over here is for this 3 level to act and allow us population inversion, the condition is that the lifetime, okay, of the excited atom over here should be such that, okay, it should immediately very fast it should decay to E2, okay, while the lifetime for decay E3 to E1 should be slow, comparatively slow. Okay. So, so over here the decay should come into picture. So, excited atoms with a very small lifetime. So, lifetime is related to a Einstein's A coefficient. Okay. We already had relationship. So, over here A 3 to 2, correct, 3 to 2 spontaneous emission is nothing but 1 upon tau 3 to 2, is not it, and lifetime is short, tau 3 to 2 is very short lifetime. So, the probability that spontaneous emission will occur from level 3 to 2 is very high basically. Okay. A 3 2 represents indirectly Einstein's coefficient A represents probability of spontaneous emission indirectly, chance. Okay. Similar to B 3 2 is the probability of stimulated emission, is not it. Okay. So, and see it is also possible that we can have A 3 1, is not it, A 3, but A 3 1 is quite low. Let us assume what it means, tau 3 1 will be very large. Okay. Lifetime for excited atom right is different depending upon energy level interactions, and if tau 3 1 is quite large, that means spontaneous emission corresponding to E 3 to E 1 will be slow, correct, lifetime is large. So, spontaneous emission will be slow. Okay. Probability of occurrence of spontaneous emission from level 3 to level 1 will be very less. Okay. While here this particular material has a characteristic such that this is fast, okay, quite large, tau 3 2. Okay. So, tau 3 2 is quite large compared to tau 3 1. Okay. If a material is such, then what will happen? Excited at what happened? Okay. Excited atoms will immediately go from level 3 to level 2, correct. Probability is very large, that is why it will go. Okay. How many will go depends upon population, etc. So many other parameters as well, but it will go right quickly. So, excited atoms over here will immediately go here. Okay. So, this level E3 will be approximately empty, right, when you compare with E1. Is it okay? Are you understanding? Okay. 1, 2, 3, from I am pumping photons with photon energy nu 1 3. So, atoms are getting excited to level 3, but level 3 becomes empty as the probability of its excited atom going to the level 2 is very large through spontaneous emission. So, all this will emit some photons spontaneously and will come to level 2. Is it okay? Hmm. Huh. No, don't get confused with semiconductor. And one more thing, I'll just you don't worry, figure is not wrong, but I want to change the color. Okay, this color only. Okay, just because that will help me. I am drawing it with this. Okay, first thing, and this. Okay, this, and the other colors. That's okay. It's available from the available color. Yeah. Now your question, please. See, indirect band gap material and direct band gap material, semiconductor ones, are different from what at present we are talking about. In case of indirect band gap material, electron hole pair combination results in recombining electron with hole will result in terms of a photon, because electron will lose the energy from conduction band, it will come to the valence band, it will lose the energy, and that energy is getting converted into photon, light energy. Is it okay? When it is coming down, two things has to be conserved, energy conservation and momentum. So, this when electron is combining with the hole in a direct band gap material, the hole momentum and the electron momentum are almost the same. Okay. So, there is not much of momentum loss and photon is emitted with the momentum matching with this, right, difference whatever. But if there is an indirect band gap material, the electron this thing is for momentum is, let us say, large, much larger than the hole. So, electron will have to match. So, there is some momentum loss, okay, combined with it, and since such processes are involved, the efficiency of the photon conversion reduces. Is it okay? Here we are not talking about any such momentum, we are just talking about 3 energy levels, and this are certain material has such characteristics, not that all the materials in this right universe will have similar characteristics 3. Okay. It is not that steel will have this characteristics, not wood, maybe some other material has such similar characteristics, okay, such that a particular see, and you also know that many structures will have multiple such energy levels, not that it will be only 1 or 2 or 3, correct. Multiple combinations of molecular structures will have even different complex energy levels. So, there are multiple energy levels, but some energy levels will have such characteristics, okay, and we are specifically talking about such materials, okay, at present, such that it has a very fast decay time over here, slow decay time as compared to tau 32 is much larger than tau 31, okay. But one more point, let us say E2, now when the excited atoms are, it is getting depleted E3 and all atoms are coming to E2 level, okay. The competition between E1 and E3 is not coming into picture, because E3 is always empty theoretically, right, becomes empty, all excited atoms will decay to ground second level. So, for E1 E3 is almost empty. So, which process is predominant? Absorption is predominant for E1 to E3, is not it? Absorption is predominant, okay. And decay, spontaneous decay is predominant between E3 and E2, is it okay? Now, if this E2 is a metastable level, okay, metastable level means the lifetime between spontaneous decay between E2 and E1 is quite large, much larger, okay. So, lifetime tau 2 1, okay, is quite larger than tau 3 1, much larger, okay. Then what will happen? The atom second level will be populated, right, will get populated. Why is it getting populated? Because pump energy is pumping the ground level atoms to level 3, level 3 becomes empty because of the spontaneous emission to level 2, and level 2 will get populated, okay, right. And there is no problem of stimulated emission coming into picture between level 1 and 3, it is absorption, because level 3 is empty. So, stimulated emission is neglected, is it okay, is it, am I fine? However, this population at level 2 will keep increasing, this all this excited atoms will come to right to this level 2, okay. So, indirectly I can create by pumping enough energy, pumping more and more photons such that this N1 will get depleted, right, and N2 will get populated, okay. So, there is a way that it will become N2 can become N1 if I keep pumping, okay. And if N2 is greater than N1, we will see that amplification is possible, stimulated emission now, right, amplification, stimulated emission anyway is present, but because N2 is greater than N1, amplification will be possible. So, amplification will be with corresponds to H nu 2 1 or 1 2, correct, 2 1 or 1 2, is not it? Photon, photon energy is different, input photon energy is H nu 1 3, is not it, correct, pumping is 1 3 photon energy, photon frequency, while output stimulated emission dominant and amplification is dominant with nu 1 2, is it correct? Correct, 1 2, right. So, what was not possible with 2 energy level, now it is possible. Any question? All right, is it okay? However, the population at N2 has to be, means I will have to pump so much of energy, so that population at N1 becomes less than half of its population, then only there is a competition between N2 and N1, is not it, right. But I will show you another diagram which is 4 level system, and you will see that we need not even pump to the level that population at ground level becomes half of its or less than that. Before that itself we can achieve population inversion, okay. So, how is it? It is quite simple, but let us, right. So, now we will draw 4 energy levels, okay, 4 energy levels. So, this is E1 with population N1, E2 with population N2, E3 with population N3, E4 with population N4, isn't it? And as we pump this frequency of the photon, incoming photon H nu 14, so it gets pumped. This is very fast, okay, very fast. So, okay, this is very fast, and from here to here, okay, is also very fast. So, what is first of all tau 4 3, correct, tau 4 3 is much higher than sorry tau 3 2, okay, sorry, 4 3 4 3 tau 3 2, I am so sorry, it was a mistake here, it should have been less. When I say fast means not increase, but tau is shorter, isn't it? Okay, I will correct this, okay, here please, this, right, it should be like this, correct, tau should be short, okay, I am so sorry, very sorry, and tau 2 1 is correct, it is much larger, okay, much larger, okay, fine. Here tau 4 3 should be very short, then tau 3 2 as well as tau 4 1, isn't it? So, what will happen? All atoms, excited atoms will end up here, isn't it? From here they will come here and then they will immediately come down to this level, is it okay? And the N2 level, E2 level rather is above the ground level. Okay. So, as per Boltzmann law in thermal equilibrium, it will be almost empty, isn't it? Population will be very small. Over and above, the decay is spontaneous decay is also fast. So, it will remain empty theoretically, it will remain empty, okay, right, practically, not but practically level 2 E2 will remain empty. So, between level 3 and 2, and this is over and above metastable level, okay, metastable. So, what it means? Tau 3 2 3 2, right, over here is much greater than tau 4 3 and tau 2 1 also, right, tau 2 much greater than, okay, right, metastable level. So, what will happen? This level is almost empty, okay. As soon as excited atoms are placed here, between level 3 and 2, correct, amplification is possible. It has to compete against 0, almost 0, nil. See, in the previous case 3 level system, the level 2 had to compete against highly populated ground level, right. That means ground level has to be emptied below half of its population, then only the level 2 will be having a larger population than the ground one, okay. But in 4 level system which is described here, the level 3 can be just populated and it will compete against empty ground level 2. So, its population inversion is very easy to achieve over here, okay. So, amplification with h nu 1 3 sorry 2 3 will be the output, right, frequency. Remember, the frequency for pumping is different from the amplification which we are seeing here, remember, that is why I changed the color, right. Frequency is large green, while what you will get is right, frequency will decrease, energy gap decreases, frequency, right, difference will be there, right, frequency will decrease. Is it okay? Are you clear? So, this is the above, right, this approach, this one is a 3 level, sorry, this is 3 level, while 4 level is, right, is this is a 4 level, okay, 4 level. And there are various gaseous, solid, liquid media which possesses such characteristics. Okay. So, there are some materials which has which can provide 3 level systems with amplification of light between any right 2 layers, 2 levels between second and ground level. And there are some media which can provide 4 level, right, through amplification of this frequency through 4 level such transitions coming into picture. Okay. So, physicists and chemists, they work on different types of media, and they have found out many such, right, media which possesses either of this, right, characteristics. The if you consider a simpler example, so the first laser, right, which was demonstrated in 1960, okay, was a ruby laser, okay, solid state material, wherein chromium was doped in sapphire material, okay, ruby material. This ruby laser is a 3 level energy system, say, okay, 3 level energy system. Subsequently, many other such solid state media were discovered which possesses either 3 level or 4 level energy systems and useful for such light amplification. And once they can they allow light amplification, then they are useful in a laser system, okay, because to achieve laser output we need light amplification, okay, and for that we need a medium, and the medium allows light amplification through their energy levels. Okay. So, ruby is one. Like that, there are various other solid state crystals. So, for example, neodymium, okay, doped, yttrium, aluminum, Y3, Y3Al5O12 is known as YAG material, yttrium, aluminum, garnet, okay, yttrium, aluminum, right, garnet compound, okay, is the matrix. Like here, sapphire is the matrix, chromium is the ion which is in fact responsible for such transitions coming into picture, and then the corresponding energy levels are important as 3 level system. Here neodymium 3 plus is the ion which is responsible for 4 level energy system, okay, 4 level. And since you know that in 4 level your pumping need not be very harsh, pumping can be small, still population inversion can easily be achieved between level 3 and level 2, because both of them are above ground level, right, both are theoretically almost empty before pumping. Once you start pumping, the level 3 over here will become populated with population larger than the level 2, right, with a very small amount of pumping also. So, 4 level system is quite effective and easy to achieve, okay, easy to achieve and efficient. So, neodymium YAG survived, right, while ruby slowly its laser, right, as now very few research teams might be using it, mostly it is neodymium YAG laser. Like this, there are various other materials, solid state materials, they allow such transitions, okay. We will try to see some of those examples with this, and similarly there are such gaseous molecules also, combinations of gaseous such as helium, neon, laser, or CO2, right, laser, or excimer lasers. Okay, excimer materials are there, some materials, excimer materials, they allow such gaseous materials, allow the amplification. Of course, there, in order to excite this molecules, gaseous molecules, we use electrical discharge. Okay, we create discharge in the medium, and then that discharge provides energy for electrons to, or atoms to get excited, go to higher levels, etc. But in case of solid state materials, right, it is no electrical discharge, it is we provide photons of pump frequency matching with the energy pump, right, this photons we provide, right, this photons which energy is matching with the pump energy band, pumping band. Okay. And those photons in turn, so its pumping is through optical means, not through discharge. Okay. Similar to the solid state material, there are it is a semiconductor material which is also right solid state. There the pumping is not electrical, but through electrical, right, potential what we apply, electrical, right, we did. So, if it is semiconductor based material, we use electrical input as the pumping. Okay. If it is a crystal, optical crystals, if they are solid state materials, then we use optical pumping. Okay. Gaseous material, it is more mainly electrical discharge. Liquid media are also there, which are of different dyes, etc. Different dyes are available. They also get excited through optical input. Okay. So, optical light interacts with the liquid media, excites the molecules, right, to particular energy levels, etc., and then we will be able to observe 4 level, right, based emissions, etc., or 3 level depending upon the medium. Now, so like this there are many, we will try to see some of these examples quickly. We will not go into details of how energy levels are derived, etc. It is physics, they have worked on it. We are just trying to see which particular energy levels are important for us, right, as the outcome, as the output wavelength. Okay. And remember that this energy levels, difference between energy levels will decide the frequency of the light electromagnetic wave which gets amplified, is not it. So, that difference will decide the photon energy. Okay. So, if we consider, okay, as I told you, that there are some material with a 3 level system, there are 3 materials with 4 level energy systems. I already explained to you this part. However, remember, as I told you, pumping frequency is quite high, large. Okay. So, pump energy is provided, and then there is a decay, and then what we see, the output wavelength whose frequency will be lesser than the input frequency. Of course, if it is more, means energy conservation will also not be able to play the role, is not it, basically it should be less. Okay. So, that is why right, E13 will be very large, E1 means the energy gap between, right, as compared to the E21. Okay, that is, so photon frequency. Now, this is what I have shown here on the left hand side of, right, is the energy level, this schematic mechanism, while on the right hand side the real energy levels of this helium and neon which are used for transition. Okay. And the bottom one is the schematic of the helium neon laser unit. Okay. When we use helium neon laser, we may not be able to see all these components such as electrical discharge combinations or etc. We will not be able to see. However, so right, first of all, if you see here, it is a neon atom, okay, which allows basically a laser transition. Okay. However, energy transfer takes place through helium atom. So, when you provide electrical discharge in a mixture of helium and neon, okay, with helium concentration 5 times that of the neon, and overall total pressure is 2.5 torr, very small, right, it is in vacuum condition, almost very small amount of helium and neon, right. These molecules are sorry, not molecules, the normal atoms are all just inside this tube. They are not interacting with anything, right. Helium and neon are inert gases, so they will simply go around in this. And but when electrical discharge is provided, the electrical discharge energy will excite first helium atom very easily, okay, and helium will get excited, and through the collision, okay, between helium and neon atoms, this energy transfer takes place to a particular neon energy level. So, helium will get excited to, let us say, this energy levels, specified energy levels of helium, and from this, the through the collision energy transfer will take place to neon. You may ask, why can't I excite neon, right, atom as it is through electrical discharge. So, the excitation should be possible, not an issue. However, it is not efficient, okay, as compared to helium, right. We can easily excite helium, and energy level of a particular helium where it gets excited matches with the neon's particular energy level, okay, right, and that is why energy transfer is quite efficient. Okay. And then when the excited atoms through energy transfer comes here, then they go to another level, and from here, so they go from helium to neon, from neon to certain, right, level, and return back to the ground level. So, this energy levels are similar to what you see in terms of 3 level energy systems, correct, 3 level energy systems. However, here the population inversion is, right, between neon higher level and neon's lower level over here, okay, the population inversion takes place. Now, the problem with this helium neon laser is, when the electron, when excited atom returns very nearer to the ground level, there is one intermediate level where everything gets settled, fast decay happens between these two levels, or these two levels, and most of the excited atoms comes here and they remain here for long time, okay. The lifetime is quite long. So, what happens, it is very nearer to the ground level, but slightly above. So, the population inversion over here does not allow, right, this very high energy efficient, I mean not efficient, but very high pump power to be excited, okay, and we have to bring this back to the ground level. So, the tube size through should be small, so that excited atoms over here will interact with the wall, lose its energy and come down to the ground level, okay. Very small energy differences there that will be lost due through these collisions between. So, the volume of the tube should be small, and if the volume of the tube is small, the amount of power which can be extracted from that lasing medium is also limited, okay. So, the output power is of the order of few tens of milliwatt from helium neon laser, but it allows a particular frequency to, right, laser output at a particular frequency, particularly green color 632.8 nanometer is sorry, not green, I am sorry, red color, right, red color 632.8 nanometer, red color output is possible to achieve, okay. And it also has some other wavelengths where it can provide output at different right frequencies. However, the prominent right outcome is that corresponding to the red, right, light. So, the helium neon laser has a red color output 632.8 nanometer, and it is very well defined in terms of a particular frequency. Okay. So, it is right very well defined in terms of output at red color, okay, and with a very specific wavelength of 632.8 nanometer, right, it is so specific. And argon will skip, carbon dioxide is another such, right, CO2 leasing material. Now, carbon dioxide this energy transfer is through various types of vibrations, okay, of CO2 molecule. See, unlike helium neon where they are atomic right levels, here CO2 itself is molecule, and COO they have different combinations. So, oxygen can, right, symmetrically oscillate, I mean can go away, come near, go away from C. So, it is symmetric oscillations. There is a possibility of bending of this bond structure. Okay. So, bending, then there is a possibility of asymmetric oscillations of oxygen, etc. Now, first of all, electrical discharge takes place in a CO2 laser through discharge through pumping, right, to N2, okay, nitrogen. So, nitrogen is excited first through electrical discharge in a mixture of nitrogen and CO2. So, CO2 is 0.8 and to the N2 ratio is 0.8 to 1, okay, it is excited. Now, CO2 gets excited through energy transfer, and then CO2 when it gets excited, different bends will come into picture, symmetric stretching, bending, asymmetric stretching, everything will be coming into picture. However, particular energy gap, asymmetric, right, stretch over here, and matching with bending and symmetric stretches over here will result in population inversion and provides the output wavelength corresponding to 9.4 micrometer and 10.6 micrometer. Okay. Over and above, this band gaps have multiple vibration bands, okay, within that small this vibrational bands, etc. So, what happens is the output wavelength, right, can be tuned by small amount, the frequency can be tuned, okay, within a particular wavelength range. So, when I say 10.6 micrometer, I can tune the CO2 laser few 100 nanometers here and there, okay, few tuning is possible. Tuning is possible because which transition plays the role for this, right, output wavelength, and subsequently it decays back to the ground level, and very large volume of CO2 can be excited, okay, and CO2 is available, plenty of CO2 is available, right. So, then right, it is possible to even generate CO2 to get the CO2 from atmospheric this thing and use it for such purpose, etc. And this CO2 laser in fact was discovered by Sikhen Patel, okay, right, who is in USA, right, Indian born, but USA in 1964 or so, 1962 or 1964, that was the laser which was, and now it has various applications for industrial applications, etc., for high power, right, lasers at CW, and there are excimer lasers. One more last, and then we will, right, continue tomorrow. This is also it is a gaseous laser, excimer laser is also gaseous laser. Okay. However, the term excimer is used because it is a mixture of argon and fluorine, okay, mixture of the gaseous molecules are argon and fluorine, krypton, or fluorine and argon, or fluorine and xenon and chlorine, etc. So, it is noble gas mixed with halogen, right, halogen gases, okay, when mixed. And when the discharge is provided, what will happen, this F2 fluorine, right, or chlorine etc., gets to it becomes radical. Okay. And noble gases also they become radicals plus K plus and fluorine or chlorine minus. Okay. And these radicals are short lived, very short lived, few nanoseconds, but then when they interact and form KRF, they can interact with highly reactive fluorine will interact with this Kr plus or argon plus and forms KRF radical or argon F. So, I am so sorry, the Kr ions, fluorine ions, they interact to form radicals. Okay. This radicals argon ARF radicals or KRF radicals are short lived, but they immediately go to a metastable level. Okay. And at ground level naturally there are no such KRF radicals at ground level. So, population inversion is easily achieved and the laser output is seen. So, why they are known as excimer? Because these krypton plus here or argon plus here ions and fluorine minus ions, they are all excited they are known as excited dimers. Okay. They are all excited dimers. When they combine, they give out a lasing operation. Okay. And that is why excimer laser. And this laser provides output wavelength in the UV region. Okay. Different combinations argon fluoride, krypton fluoride, xenon chloride, xenon fluoride. Okay. And this combinations provides different energy levels for laser output. Okay. And 193 nanometer, 248 nanometer, 308, 350. These lasers have applications for therapeutic applications. Okay. We will see they may not be useful for sensing applications, biophotonics, yes it is, directly sensing no, but it is towards right therapeutic applications to allow ablation of tissue, to remove the tissue or to cut through the tissue, to do this, all such things are possible. Okay. So, excimer lasers have a very good that way very good use. CO2 laser is also very useful, although it is wavelength is 10.6 micrometer. It is not very easy, right. So, but therapeutic applications CO2 lasers are useful because it provides heat, right. Basically the tissues will absorb this light at 10.6 micrometer and the thermal effect comes into picture, which is basically heating etc. So, CO2 lasers and then subsequently these excimer lasers, right, are useful. Excimer lasers, the advantage is they are in the UV region. So, focusing characteristics are quite different, very right. It can be focused to very small spot size, wavelength order, right, focusing as compared to the CO2 laser, because the wavelength is quite large 10.6 micrometer. So, you can focus to a beam, but its diffraction limit will be much larger than the UV laser beam. Okay. So, the focusing characteristics are quite different. Okay.